I'm Sarah Worden. I'm a graduate student at UCLA, and I just want to say thank you for giving me the opportunity to give a talk today. I'm really excited to share my science with you all. And so, so today I'm going to be talking about quantifying evapotranspiration over the Congo Basin using a combination of satellite-based deuterium and gravity measurements. I'd like to thank my collaborators, my research advisor, Rong Fu, as well as John Worden, Anthony Bloom, and Paul Levine from JPL. So as a bit of background about the Congo Basin, it hosts the world's second largest rainforest, as you can see from this picture here, which makes it pretty important to both global and regional carbon and water cycles. But there's also a very big lack of in situ data. So this makes it one of the least studied places in the world. And so that makes it a very interesting but challenging place to research. For example, evapotranspiration, or ET, as you can see from this figure here, it's not well constrained over the tropics, and specifically for the Congo Basin. This figure here shows model estimates of ET from ICAM, ET from AERO5 reanalysis, ET calculated using water balance methods from Burnett et al. 2020, and ET from a remotely sensed data set created by Joshua Fisher. And as you can see here, they all do somewhat capture the seasonal cycle of ET, and that they're able to capture both of its rainy seasons in spring and in fall, but they disagree widely in the magnitude of the seasonal cycle. And so we need to come up with a way to better constrain ET estimates. And before I get to that, I want to give a bit of research motivation for quantifying ET. So observations showed a recent decline in rainfall in the Congo Basin, as you can see from this picture here from Zhao et al. 2014, where multiple precipitation data sets show a decline in rainfall from the year 2000, and then also changes to the rainy season lengths. So the summer dry season is expanding in length at the expense of the spring rainy season. And so this is especially concerning considering that the Congo Basin is also the driest rainforest in the world and is home to a lot of anthropogenic forcing, such as some pretty intense biomass burning. And so this means that it's possible that the Congo Basin may be more vulnerable to climate change than the other major tropical rainforests of the world, the Amazon. And so what we want to do is to test whether changes in evapotranspiration as an important source of atmospheric moisture for precipitation. So changes in that can lead to changes in precipitation. So previous studies have shown that atmospheric moisture over the Congo Basin comes from both evapotranspiration, in this case in the tropics, mainly transpiration, as well as advected ocean water from the Atlantic and Indian Oceans. I recently published a paper actually showing that evapotranspiration was the main source of atmospheric moisture for the Congo Basin. And we did this using water vapor isotopes. And that's because the isotopic signature of water vapor that comes from plants, so from land, is different from that of water vapor that comes from the ocean. But atmospheric processes, such as rainfall, can actually mask that isotopic signature, since they can affect the heavy water vapor content of the air parcels. To get around this masking, we compared deuterium observations from the test satellite to isotopic atmospheric mixing models, as you can see in this figure here. And so specifically, the model we're concerned with is this top green line right here. That is a model that is representative of mixing processes over land. So what would happen to an air parcel from land as it rose up and mixed with the air around it. And so the idea is that any of the observed observations of the ratio of HDO to HDO, or HDO to H2O, what we call delta D, if any of those observations are above this land-based mixing model, they have to have come from land. And so we came up with a metric, F, which is the fraction of those observations above this mixing model. And what this means is the higher F is, the more ET contributes to atmospheric moisture. And so as you can see from this figure here, F is above 50% for most of the year, meaning that ET is the dominant moisture source during those times. You can see that F is below 50% during the rainy seasons. And so I want to note that it's still entirely possible that ET is still the dominant moisture source during these rainy seasons. It's just that the atmospheric process, rainfall, tends to deplete delta D. And so that means that F could be lower than it actually is seen. And so in summary, what this means is that we're able to use water vapor isotopes to show that evapotranspiration is the dominant moisture source for the Congo Basin. But now we can actually quantify basin scale evapotranspiration by calibrating air-based water vapor isotope measurements to gravity measurements and river discharge. And I'm going to briefly go through this methodology. So Bailey et al. 2017 found that normalizing satellite observed HDO to HDO ratios to a reference concentration of 4 millimoles per mole co-varies with vertically integrated moisture flux divergence, which is this term here, div in brackets in the tropics. So they were able to find this a linear relationship between this normalized ratio called DDO4 and moisture flux. But we know from the water balance that this vertically integrated moisture flux divergence is also equal to the net of evapotranspiration minus precipitation, meaning that a linear relationship exists between DDO4 and ET minus P in the tropics. And we wanted to investigate if this would be the case over a smaller area, the Congo Basin. We first did this using the ICAM model. This figure here shows DDO4 and ET minus P as estimated by this model. And you can see that there is indeed this linear relationship for the Congo Basin. But the next step is to see if the observations can capture this linear relationship as well. We could have used a remotely sensed evapotranspiration and precipitation, but remember that evapotranspiration is not well constrained over the tropics, and to some extent as well precipitation. So we turn to the water balance again, where ET minus P is equal to the net of river discharge, where Q is river discharge measured by a gauge station at Kinshasa Brazzaville, and it captures 98% of the Congo Basin river discharge. And then also change in terrestrial water storage, where here S comes from Grace terrestrial water storage. And so we looked at the relationship between that, Q over A, and DSDT with DDO4 from the AIRS satellite instrument. And you can see that there is still this linear relationship that is captured by the observations. So using this linear regression, we are therefore able to calculate the water balance over the Congo Basin on a basin scale. And as you can see here, the water balance is mostly negative throughout the long-term record and always negative during the, its seasonal cycle, which is consistent with what we know about what we would expect from the tropics. And then finally, the last step was to calculate ET. So we took our calculations of ET minus P from our deuterium, gravity, and river discharge measurements, and then added precipitation from the TRIM satellite. And so after doing so, we were able to confirm a strong ET contribution to atmospheric moisture over the Congo Basin. This figure on the left here shows precipitation in blue, our calculated ET in black, river discharge in green, moisture flux convergence in purple, and Grace DSDT in yellow. And as you can see, evapotranspiration is the main source of atmospheric moisture for precipitation. Furthermore, our calculation of ET matches fairly well with the other ET estimates. And so I just want to really emphasize here that we're using the water vapor isotopes to really provide an extra constraint on pre-existing estimates of evapotranspiration calculated using the water balance. That's because the error in river discharge is unknown. The error in gray terrestrial water storage estimates is, well, gray is mainly precision limited, and AIR's data is well calibrated. And so with that, I get to my main points. So water vapor isotopes, we previously used them to show that ET is the dominant source of atmospheric moisture in the Congo Basin throughout the year. And now we have developed a method to use these. Sorry, my headphones turned off for some reason. Now we have developed a method to use these water vapor isotopes to quantify basin scale ET and further constrain these already existing water vapor balances. And with that, I would love to take any questions. Thank you.